6 notes, we're going to look at symmetry. So we've learned about a line of symmetry. A line of symmetry is any line that cuts a shape so that two equal parts are created. Let's say polygon instead of shape. So that's kind of your generic term. That's your line of symmetry. And the example that we kind of looked at with the questions you guys asked, with I think it was number 8, previous assignment, was what about a parallelogram? Let's say that's our polygon. And what we've learned is that if we cut a diagonal in a parallelogram, or if we actually fold the diagonal in a parallelogram, that it doesn't fold onto itself. But if we cut it, we create two equal triangles. So this triangle and this triangle have equal sides, a 1, a 2, and a 3, and a 1, a 2, and a 3, so that they are equal triangles. So this is a line of symmetry, it's just not a reflective line of symmetry, which is the next one. I'll shorten the symmetry by sim. A reflective line of symmetry cuts a polygon or folds a polygon in such a way that each part folds in on itself. The best idea is to it folds a polygon reflective line of symmetry. A great example of that is a square. It has all sorts of reflective lines of symmetry. So here's my drawing of a square. And if I fold a square along this vertical axis, the two halves will fold in on themselves, right? I can also fold it along the horizontal axis, and they'll fold exactly onto themselves. Are there any other lines of symmetry, of reflective symmetry in a square? Yeah, well, you're exactly right. Diagonal as well. Think of cutting a sandwich, square sandwich. How many ways can you cut it where you cut it in half and you could sort of fold it onto itself? Not all shapes have reflective lines of symmetry, but there are shapes that have more sides than a square that also have reflective line of symmetry. A regular pentagon is an example. Let me show you. If I fold this like this, I have a reflective line of symmetry where both halves are exactly equal. And they fold in on each other. Okay? So that's a reflective line of symmetry. Not all lines of symmetry are reflective, but some are. And we also want to talk about rotational symmetry. I think of this as, in my mind, I imagine a cartoon with somebody trying to push a square wheel. Or, in the example that I'm going to give, it's going to be a five-sided wheel. Okay? But I'm going to call this the square wheel symmetry. That's going to be my term for it, the square wheel symmetry. And that's when we spin a shape and we see how many degrees we have to rotate the shape until it sort of falls back into itself or clicks back into itself. So how many degrees does a shape have to rotate before it? I prefer the idea of clicking onto itself. Again, kind of my idea. I mean, maybe more my words than my idea. But here's what I mean by that. If I take my pentagon that I've cut out here and I rotate it, how far do I have to rotate it before it fits or clicks back onto itself? 25? 45? I think that's 45 degrees. Could be. How many clicks until it gets back to its original position? 5, right? How many degrees is that? 60. Hang on. Daniel, you have an answer for me, but I'm not looking for an answer just yet. Let me give everybody a little bit more information before you I'll let you answer though. Okay? All shapes will click back onto themselves. All shapes have 360-degree rotational symmetry. Some have less than that. So all shapes, all polygons, have 360-degree rotational symmetry. A good example of that, and in fact in our last assignment it talks about kite. A kite is an example of a shape where you would have to rotate a kite exactly 360 degrees before it fit back onto itself. So a kite, 360 degrees. But what about, where did my cutout go? What about this regular this regular pentagon? You have an answer for me?
I think it's 72 degrees.
You think it's 72? How did you come up with that?
360 divided by 5 because it has 5 sides.
You got it. That is exactly how you calculate that. On a regular shape, a regular polygon will have rotational symmetry 360 divided by, I'm going to say n, the number of sides. Running out of space here. The regular. Hang on a second. Yes, Daniel.
So if the shape's sides are greater than 360 is the decimal degree, right?
That would be correct. Yeah, so if you had 720 sides, then it would be a half a degree rotation for each one. Yeah. So in this case, with our five-sided shape, I have to rotate 360 divided by 5, which, if I can trust Daniel's math, is 72 degrees. It's exactly 72? Mm-hmm. 72 degrees. So a regular pentagon would have 72-degree rotational symmetry, meaning that's exactly the amount of degrees it has to turn before it clicks into itself the first time. What about the second time? How many degrees does it have to spin to click in the second time? How much? Nope. What's that? No, that's the first time.
144.
There you go. Double the 72, right? Yeah. And then the third time. Yes.
216.
216, I agree. And then the fourth time. 288. Good. Good. 288. And then the fifth time would be 360, right? So if I start here and I rotate, this one's going to be 72 degrees of rotation. Yes, sir.
Does that mean the angle of the corners are also 72 degrees?
Good question. What do you think looking at it?
Oh, wait, no, that's the one.
Right. You're on to something, though, and I'll show you what you're on to.
Yeah.
Let's see, what was it, 216 for the third rotation, or for the third click? And then 288. And then back around, this would be both 0 and 360 degrees. Yes.
I think it's 108 degrees.
You think it's 108?
Yeah. I did 180 minus 72.
Okay. I think you're exactly correct. Yeah. So Daniel's experimenting with it in his mind here with this pentagon. Since he's going somewhere with that, let's talk about that for a second. He just said correctly that this is 108 degrees. Oops, not 180. Each of these corners has 108 degrees. How did you come up with that exactly?
I knew that black would be 180 degrees because 208 is 360, so half of 360 is 180. And then I did 180 minus 72.
Okay, well, let me back up a little bit here for a second, because what you just said was you knew flat was 180. So I'm going to draw one of these legs out like this. Oh, sorry. There we go. In this shape, we call this, you don't have to take this notes, but this is kind of going where he's going, and it's certainly something you'll need to know at some point, but not yet. This is an interior angle. This is an interior angle right here. This guy right here, where I've drawn the line, this is called an exterior angle. If I add up all of the degrees of every exterior angle, of any shape this plus this plus this plus this plus this will always equal 360. But do me a favor. How many degrees are there in all of the interior angles on a pentagon? Yes. 5? 5 degrees?
Oh, 5 degrees, yeah. They're asking how many angles.
Oh, no, there's definitely 5 angles. If this is 108, how much is all of the angles put together? A lot, I agree. How much? I think it's more than that. It's less than 900. 108
564. Just kidding. 540.
540. Yeah. So if each of these is 108 degrees, that's going to be the sum of the interior angles. Equals 108 times 5, because we've got 5 interior angles, which is 540. The sum of the exterior angles is always 360. Again, this is a little more than what we need right now, but it kind of leads us to maybe some cool stuff. What if I wanted to know the sum of the interior angles of this shape? Yeah?
You would do 360 divided by 3.
Uh-huh.
You get 120.
So you're telling me this is 120 degrees?
You have to do 180 minus 120.
Okay. So if this is a regular triangle, this means the exterior angle is 120 degrees.
Yeah. So the interior is 60 degrees.
So what's the total sum of the interior angles? If each one is 60.
180.
180. Right. Yeah, and here's the thing. The triangle does not have to be regular. It doesn't have to have 3 equal sides and 3 equal angles. Any triangle will have 180 degrees inside. Okay? All triangles have 180 degrees, interior angle sum. What about a square? Well, one of the definitions of a square is it has 4 right angles, right? So 4 times 90? 360. So the interior angles and the exterior angles on a square are exactly the same. So interior and exterior, same number. What if I take a square and I cut it in half? What do I make when I cut a square in half? 2 triangles, exactly. And how many degrees are in a triangle? If there's 180 in each triangle, then how many is in the square? 360. What if I apply that idea to my pentagon? Notice in the square I only drew one triangle, or I only drew one diagonal, right? There's more than that in a square. There's 2 diagonals, but I only drew one, and that's specifically for a purpose. If I pick any point in a polygon, let's say I pick this point right here, and I draw all the possible triangles. Well, hold on. No, wait, I want you to see this. If I draw all the possible triangles that I can from this point, so all the diagonals, only from that one point, how many triangles am I able to make? 3, right? And in each triangle is 180 degrees. And if I add up 3 triangles worth of degrees, I get 540 degrees, which is exactly what we calculated earlier, right? So however many sides you have doesn't matter. If you pick a point, one of the vertices, this is a vertex, and you draw triangles, however many triangles you can make times 180 is how many degrees the total number of angles are inside a shape. It's a really slick trick. There's a formula for it too, but I like this better. It's more visual. Okay. All right, let's look at our task.